Okay, so let's talk about our second periodic trend. It's called ionization energy. And so I'd get this copied down up at the top while I'm talking. Alright, so ionization energy, the definition is the energy required to remove one electron. An easy way that you can remember this is that in the word, we have the word ion. And when we're talking about ions, we're always talking about adding or removing electrons. So ionization energy is the energy required to remove one electron. Alright, so write that down and then copy down this chart right here, the different trends. While you're doing that, I'm going to draw some elements down at the bottom that we're going to look at. I'm going to do our Li one again. Remember, it has one valence electron. And then F with its 7 valence electrons. And then we also have I. And I has tons of rings. And it also has 7 valence electrons. Alright, so hopefully you finished copying everything. So let's look at this chart down here and let's try to figure out our trend. Okay, so our trend as we go across, you'll notice that these numbers start to get larger. Okay, they get bigger as we go across. So for our trend for going across is that we have an increase in ionization energy. Alright, the next thing we're going to look at is as we go down. So as you go down, you'll notice that each time we go down, we see a decrease in our ionization energy. So down is decrease in ionization energy. Okay, so now we need to figure out our Y. So let's look for our first one across. We're going to be comparing Li and F as we go across, right? Because Li and F are both in our same row. Li is over here and F's all the way over here. So as we go across, why do we see an increase in ionization energy? So remember, ionization energy is our energy required to remove one electron. So think about, does F want to hold its electrons? Is it going to be harder for us to pull an electron off of F, or is it going to be harder for us to pull an electron off of Li? If you remember F likes to have a lot of electrons. It's almost full. It almost has 8. So it wants to have all of these electrons. It doesn't want to lose any because it's so full to be having 8. Whereas Li doesn't mind if it loses this electron, because if it loses it, it will have a full shell with these 2 underneath. So we see an increase because as we move across our periodic table, we have an increased number of valence electrons. And as we increase our number of valence electrons, we get closer to having 8 on the outside. And so they're going to hold on to all of those because they are so close to getting 8 that they want to keep all of them. I've heard it compared to like if you're playing a sports game and you're really close to winning, you're going to be trying really hard, right? But if you're super far behind and not really going to win, you're not going to try as hard to hold on anymore. Okay, so we see this pattern going across because we have more valence electrons or an almost full shell. Remember, if I ever do an E minus, that means electrons. Alright, so now we have to look going down our periods, or down our groups here, because you'll notice F and I, they both have 7 valence electrons. So this rule doesn't work anymore, because they both have 7 valence electrons. So they're both trying to get to 8, so they're both still holding them tight. But you'll notice how F still has a higher one than I, right? It still decreases as we go down. And that's because you'll notice here, F, these electrons are very close to the positive center. I, these electrons are way out here. We've added these extra rings, and so they're very far away. And so these electrons are going to be able to be pulled off easier because they're further away from the positive center. Whereas with F, they're very close to the positive center. It's like in football, the running back usually holds the ball very close to its body, like F, so it's harder to knock the ball out. If the running back were to hold the ball far away from its body, it would be like I, and it'd be easier for people to grab the ball. So as we go down, it decreases because the electrons are further from the positive center. Or a different way we could say it is from the positive nucleus. Alright, hurry and get that copied down or pause the video if you're still writing, because we're going to scroll up to the top and we're going to do the same thing we did, and we're going to label our periodic tables. So pull out your periodic tables and let's label it. Alright, so just like this, we're going to say an increase in ionization as we go across, and we're going to say a decrease in ionization as we go down. Okay, so that means the elements over here on this side of the periodic table usually have a very high ionization energy. If they're down here, they usually have a very low ionization energy. So again, on your test, it might ask you between O and CS, which one has the highest ionization energy? And you would look and you'd say it increases as we go across and it decreases as we go down. So things up here have a higher ionization energy. So O is going to have a high ionization energy. CS is down here. It has a very low ionization energy. Alright, that's all we have with ionization energy. We're going to do one more and then we're going to be done with periodic trends.